No. The volume is too loud, or it's okay.
That's fine.
How do you feel it?
A little bit loud.
It's okay.
Okay.
Little bit too loud. Okay. Okay. Let me tell you something before we start this. So it happened that in 2007 I had one quite important grant, a Marie Curie Excellence Grant from European Union for something which is called nanotechnology opinion centers in superconductors. And I had to find a host, and that host was the University of Birmingham, which had the equipment and had expertise for that. And with that 1.6 million euro from European Union, I built a team, and we worked there for 4 years. In the same time, Ali, we was trying to establish a strong base for superconductivity in Turkey for a very simple reason. Turkey is the country which has the largest quantity of highly pure boron from the entire world. So the fact that they want to develop here high technology equipment and not just sell raw materials, it's maybe it's a great thing. So when he tried first to organize a conference, it was in Side, which is some sort of small summer resort which belongs to Ankara University. And the conference was, I don't know, something like 200 people, 300 people, 3.5, something like that. Anyway, it was at some point, the first attempt, it was very hot, very small rooms. And after that, some people were asked by Ali, okay, give me some ideas how to improve that. And in 2 years, the next conference was close to 1,000. And from then it is growing. And it became probably apart from, I don't know, maybe UCAS, but anyway, it's among the largest conference in the world dealing with superconductivity and magnetism. And this is a great thing that Professor Gencer and Ankara University managed to create a center for excellence research in superconductivity, which is some sort of unique thing. Not many countries have a research center based and focused only on superconductivity. It's very, very important. Okay, so shall I start now with the first lecture?
Actually, it's at 3:30, so we may probably keep the schedule, or we may start straight away.
You may extend your lectures, so you can do. It's up to you.
Okay. So, do you need a coffee break?
I think we.
Maybe
later, probably.
Maybe.
Once you start, and
okay.
you may continue. Better.
Okay, as I said, I worked at the University of Birmingham for 8.5 years, and after I get rid of, let's say, family obligation to get my children educated, one graduated from School of Economics and is working now for PricewaterhouseCoopers, and the other one is last year doing PhD in chemistry. I moved back to my home research institute, which is National Institute of Materials Physics in Bucharest, in Romania. Quite a nice place. Now we are developing with European Cohesion Funds, brand new Center for Advanced Materials Surfaces and Interfaces. So it's a good research place to do there. Okay, so my lectures will be based on this saying by this guy, everything should be made as simple as possible, but not simpler. So I will try to keep as little math in my talk, because I had some Russian theoreticians friends and if they do not put 3 rows of formula, they are not happy. I don't like that. And I'm sure you don't like that. So the contents of my first lecture will be an introduction in which I will talk about type 1 versus type 2 superconductors. Then what are vortices? What is spinning? And for practical applications, there are 2 important things. One, pinning force density, and the pinning potential. And we will discuss about these things in the first lecture, which should be about 45 minutes. If we are longer, we do have enough time. Now, type 1 superconductors. They cannot be penetrated by magnetic flux lines, so they have a complete Meissner effect. So when they are in the superconducting state, they are not penetrated by the magnetic field. Because of that, they have only one single critical field at which the material ceases to superconduct and becomes resistant. And they are usually elementary metals such as aluminum, mercury, lead. So if we look here at the plot of -4 pi magnetization, so the magnetization and multiplied by this constant, versus the applied field, when it is in a superconducting state, the magnetization follows exactly the applied field, and then at a certain field, which is the critical field, magnetization drops to 0, and the material stops to be a superconductor and behaves like a normal metal. If we look on the internal field B inside the material, that magnetization, which because of this minus sign you see, it opposes the applied field, magnetization inside the sample is 0 up to the certain critical field, and then magnetization, the internal field follows the applied field or the external field. So inside a superconductor of type 1, up to the critical field, we do have 0 internal field, and we have a magnetization which is exactly opposing the applied field. Now, about type 2 superconductors. They have a gradual transition from superconducting to normal state with increasing magnetic field. Now, they usually superconduct at higher temperatures and fields than type 1. And between Meissner state and normal state, there is a very large mixed or vortex state. We will see what is that. And they have 2 critical fields, upper and lower. Now, if we talk about very thin films, they happen to have a 3rd critical field because geometrical factors can induce some other vortex dynamics. So very thin films, they have actually 3 critical fields, the bulk one, HC1, and HC3, which is the field, which is the highest field of the 3 critical fields. These types of superconductors are usually metal alloys, intermetallic compounds, complex oxides, for example, copper-based hydrogen superconductors, and more recently discovered peptides and chalcogenides. Now let's look what happens when we apply a field. If we look at the magnetization, meaning the response of the material when a field is applied, and again we plot it multiplied by -4 pi, we have a straight line with slope 1 up to a lower critical field which is called AC1. And you see between this 0 field and HC1, we have the true Meissner state or the true superconducting state. Unless type 1 superconductors, now if we further increase magnetic field, the applied magnetic field, we have a gradual decrease of the magnetization, not an abrupt one. And that goes to 0 at a much larger field, which is the upper critical field, HC2. And between HC2 and between HC1 and HC2, we have the so-called vortex state or mixed state. When we go further with applying field, we go back to the normal state, which is similar to this one. It is very important to look at the following thing. We still have something which is called the thermodynamical critical field. That thermodynamical critical field will be found when we do the calculation of the free energy between the normal state and superconducting state, and this Hc is actually square root of Hc1 multiplied by Hc2. We cannot see it in this type of measurements, but the thermodynamical critical field still exists also in type 2 superconductors. Now, if we look at the internal field in the material, between 0 and quite a small lower critical field, BC1, internal field inside the material is 0. After we increase the field further, then we do have an internal field in the material. And we will see later on that that internal field in the material is actually formed by flux quanta, which are called vortices. And when we reach the upper critical field, we get back to the straight line with the slope 1, and we go in a normal state. Okay, if we look at the classical superconductors, why I'm saying this classical, we're talking about the superconductors which are were discovered before the peak rates, and that means the low DC superconductors. So type 1 superconductors, we have a phase diagram in which we have here TC at 0 field, and we have critical field which depends on the temperature, and this region is a superconducting region. This one is normal. If we look at the type 2 superconductors, as I said, we have two critical fields. Both of them depend on the temperature. This is the lower critical field, and this is the superconducting phase or Meissner phase, and this is the mixed phase, which is between the BC1 as function of temperature and BC2 as function of temperature. Now, this mixed state, well, some people like this one. Some people said, okay, this is the Meissner state and this is the mixed state or vortex state. Now, in the mixed state, we do have true superconductivity. If you pass a current not larger than a critical current, we can transfer power without dissipation. So it is a true superconductor, even if we have inside a magnetic field. But from the old times, superconductivity means that no field inside, from the Kabernik-Ohm's time. Now, we have two lengths in the superconductor. The first one is the penetration depth. Now, the superconductor, they are diamagnetic materials, so we have no internal flux. We've seen that B inside is 0. But in order to repel the applied field, we need to create a field which opposes the external field. And that field is created by some currents which are confined to the surface. And that currents at the surface, they create a field which opposes the applied field. And because these currents must flow in a finite thickness, the currents are going like this. So deep inside the superconductor, we do not have any current, but at the surface we have a current which creates a magnetic field which opposes the applied one. And this current or the magnetic field inside decreases from, and the external magnetic field at the surface, B at surface at x equals 0, decreases to 0 inside, because we have seen that inside the material we have 0 internal field, and at the distance in which B of 0 decreases by the Euler number, E, this is called the penetration depth. So this is how magnetic field varies inside a superconductor, and for very large x and divided by lambda, of course, current goes exponentially to zero. So this is the first characteristic length in the superconductor, and it is the penetration depth, and it relates to the circulating supercurrents which create the opposite magnetic field, and also to the length scale in which the magnetic field drops to zero from the applied external one. The second characteristic is the coherence length. And this is this length characterizes the distance over which the superconductive wave function can vary, can modify its amplitude without undue energy increase. But also it can be viewed as the distance over which the superconducting carrier's concentration decreases by Euler's number E. So if we look at the interface between a normal and a superconductor, what we have? In the superconductor, deep inside, we have the maximum carrier concentration, and which is proportional to square of the amplitude of the superconducting wave function. And of course, in the normal phase, we do not have any superconducting carriers, so that it should go to zero. The distance over which this goes from the maximum to zero, this is the coherence length. And if we look here, we see also that the lambda, the penetration depth, is the length over which the external field drops to zero at the normal superconducting interface. And if we compare these two characteristic lengths, this good lambda parameter is k equal lambda over psi. And it has been shown through analysis of the free energies at the interface between superconducting normal that if k is smaller than 1 over square root of 2, we have type 1. Or if k is larger than 1 over square root of 2, then we have the type 2 superconductor. Let's see, why is this? Okay, let's first take the case in which psi is larger than lambda. So what we have here? We have the normal and the superconducting interface. And we have here the magnetic flux density, which is large in the normal region because there is the applied field, and goes to zero in the superconducting part. The variation is characterized by lambda, the distance over which this magnetic flux energy decreases by Euler's number. On the other hand, the number of superelectrons has a maximum deep inside the superconductor and goes to zero in the normal state. And the characteristics length over this variation happens is psi. So this is what we have. Now, free energy density. What we have? We have a positive energy from the magnetic contribution. And this is 1 over 2 mu 0 hc squared. And this is how it varies from maximum to zero, and this is the distance lambda from the magnetic field. Now, why happens that we have superconductors? When Cooper pairs are formed, the free energy in the superconducting part it's smaller than the free energy of the metallic, the normal part. So obviously, the free energy in the superconducting part is negative from zero. So this is the and from the free energy discussion of the critical temperature and so on. These two parts are equal. So this is the condensation energy which equals the magnetic contribution. So deep inside the superconductors, this goes back to zero. And if we add these two, we have this thing. So the free energy of the normal, free energy of the inside, because we have the Bose-Einstein condensation, but at the surface, what we see here, we have a little region in which the free energy has a maximum. What does it mean? It means the system will hate to have interfaces between superconducting and normal phase. But if you are forcing it to have also normal phases, what we'll do, we'll try